So, have you ever wondered if historical data can actually predict the future? I know, it sounds a little bit like magic, right? But honestly, whether we're talking about forecasting the stock market or trying to figure out next year's housing prices, there are mathematical patterns literally hidden inside our everyday data, just waiting to be uncovered.
Welcome to The Explainer. Today, we're going to be decoding one of the absolute most powerful predictive tools in all of data science, and that's regression analysis. We're taking a journey from drawing really simple lines on a graph all the way up to building complex models using multiple variables.
Here's our roadmap for today. We'll start with an intro to linear regression, move into ordinary least squares, talk about measuring our mistakes, dive into the coefficient of determination, scale up to multiple linear regression, and finish off with some essential regression assumptions. All right, let's jump right into section 1, Intro to Linear Regression. So what actually is regression? Well, it's basically our primary statistical tool for analyzing the relationship between an outcome we really want to predict, say a house's price, and the independent variables that we think influence it, like square footage. Our main goal here is to uncover causal relationships. We want to understand exactly how tweaking one thing impacts another. Okay, let's dive into this. In simple linear regression, we essentially take our actual observed data points and use a y-intercept along with a slope to draw a best-fitting line right through the middle of them. The entire goal of these regression models is to find that absolute best-fitting line that truly represents the overall trend of reality. Which brings us perfectly to section 2, ordinary least squares explained. Because once we draw that line, how do we mathematically know if it's, well, the right line? Notice that there's something called random error. It's the literal gap between what our model predicted on the line and what actually happened in reality. And, these residuals or errors, they're just completely inevitable when you're mapping out real-world data. So to solve for this, we use a method called ordinary least squares, or OLS. You can think of OLS as the mathematical engine of our model. It calculates the difference between our observed and predicted values, squares them, and then finds the specific line where the sum of those errors is at its absolute minimum. It's kind of like a giant rubber band pulling the line into the tightest possible fit, just to shrink those error gaps down.
Moving right along to section 3, measuring our mistakes.
Now that we've gone ahead and minimized those errors, we need a standard, reliable way to grade our model's mistakes. On one side, we have mean absolute error, or MAE. This simply quantifies the average absolute difference between the predicted and actual values. It's super robust and straightforward. But on the other side, we have root mean squared error, or RMSE. Now, RMSE is a fantastic general-purpose metric, but compared to MAE, it actually amplifies and severely penalizes larger errors because of how it mathematically squares the differences. Basically, if your model makes a massive miscalculation, RMSE acts as a strict penalty system to let you know loud and clear. Next up, section 4, coefficient of determination. And this brilliantly illustrates our next point. Beyond just looking at absolute errors, we have to score our model's overall goodness of fit using R-squared. By comparing the sum of squares due to regression against the total sum of squares, R-squared quantifies exactly how much variation in our dependent variable is actually explained by our model's line. It gives us this really solid, quantifiable measure of just how well our actual data points align with our fitted regression line. All right, let's scale things up in section 5, multiple linear regression. Because in the real world, outcomes are almost never driven by just one factor, right? Predicting a house's price isn't just about square footage. It's about the number of bedrooms, the age of the property, the neighborhood, the whole shebang. And that is exactly why we use multiple linear regression. It allows us to mathematically quantify the exact combined contribution of several independent variables all at once to predict the outcome of our dependent variable. But there is a fundamental limitation with standard R-squared when we do this. It literally always increases when new independent variables are added, even if those variables are completely 100% unrelated to the response. This leads to artificially inflated, misleading values. So, to fix this, we rely on adjusted R-squared. This modified version directly addresses that flaw by mathematically accounting for the actual number of variables. It basically keeps our metrics honest, so we can accurately compare models of completely different sizes. Finally, let's look at the rules of the game in section 6, essential regression assumptions. So, the crucial point is this. Before you run any calculations whatsoever, you have a strict checklist to clear. The relationship absolutely must be linear.
You must have no multicollinearity, meaning your variables aren't overlapping. You also need homoscedasticity, no autocorrelation, normally distributed errors, and exogenous variables. Plus, there's a golden rule. You really need a substantial sample size of at least 20 data points per variable.
Let's zoom in on one of the biggest hurdles here, homoscedasticity. I know, it's a total mouthful, but it simply means the variance of your errors must be exactly the same across all of your observations. Think about it. If your errors wildly expand in one section of your data and then shrink in another, your model totally loses credibility. We absolutely need that variance to remain consistent. Another really dangerous pitfall is autocorrelation. This measures the degree of correlation between a variable and a lagged version of its own past values over time, ranging from -1 to +1. Our baseline assumption requires zero autocorrelation. Why? Because if our data points are suspiciously related to their own past values, well, our observations are no longer independent, and that severely undermines the entire integrity of our regression model. Wow, we have journeyed all the way from the basics of drawing simple, best-fit lines to understanding the really strict assumptions required for multidimensional analysis. The math here is highly structured, and the parameters are crystal clear. So knowing the rules and tools we've explored today in this explainer, how will you use multiple linear regression to uncover hidden relationships in your own data? It's a lot to think about. Until next time, keep analyzing and keep learning.